Hi everyone, here are your notes for section 5.4. Just trying to get myself organized here. So what we're going to be getting into today are multiple different types of identities that you can use. So again, if you're creating that identity list and compiling them all together, you probably are going to want to make sure you have these added onto it. So I do have them all filled in for you. I'm actually going to have you do the derivation of them yourself. So it is all possible, but I kind of want you to discover them and see where they come from yourself. So we have what we call the double angle identities. So when you double an angle, you get the following results. So our double angle for, I think I have a pointer here. Is that going to do anything? Or nope. Yeah, maybe I don't want to do that. Done. Okay, so our double angle for sine of 2u is equal to 2 sine of u cosine of u. Our double angle for cosine has multiple variations. You have the cosine squared of u minus the sine squared of u. And then that can be derived into 2 cosine squared u minus 1, which also can be derived into 1 minus 2 sine squared u. So those are all your possible values for your double angle of cosine. And then your double angle of tangent, tangent of 2u is equal to the tangent of tan u minus 1, or all over 1 minus the tangent squared of u. For your half angle identities, so we've doubled, now we're going to get into half. Your half angle identity for sine is equal to plus or minus the square root of 1 minus cosine u over 2. For cosine, it's plus or minus the square root of 1 plus cosine u over 2. And for tangent, you have all of those following options. So plus or minus the square root of 1 minus cosine u over 1 plus cosine u. If you multiply by the conjugate of the denominator, you can simplify that to 1 minus cosine u all over sine u. And if you multiply by the conjugate of the numerator, then it goes to sine u all over 1 plus cosine u. Okay, so we've got double, half angle identities, and then we have our power reducing formulas. So if we have the sine squared of u, that's going to be equivalent to 1 minus cosine 2u all over 2. If you were to take one of these guys right here, let's say this one that has the sine squared in it, and solved it for sine squared, that you would end up with this ratio. Or actually, I guess if we would use, yeah, we would have that ratio. Right? I forgot the cosine 2 years there. If we did the same thing for cosine squared, if we solved for our cosine squared here in this equation, then we would end up with this ratio, and then same with our tangent. So there's your tangent squared u. Ends up with the ratio of 1 minus cosine of 2u all over 1 plus cosine of 2u. So I'm actually going to derive, example 1 here is the derivation of our first double angle. So let's go through this together so you can kind of get an idea of where it's going. So the sine of 2u is the same as the sine of u plus u, right? Which, if I use my sum identity for sine, the sine of alpha times the cosine of beta, which in this case is just both u's, carry the same operation, gets us the sine of beta, which in this case is u, cosine of alpha, which in this case is u, which turns out to be 2 sine u cosine u's, which is equal to 2 sine u cosine u. Oops, forgot my u. U cosine u. QED. Done. For number 2, we're going to show that the cosine to the 4th power of theta minus the sine to the 4th power of theta is equal to cosine 2u. So I notice here that I have a difference of squares, which really is cosine squared u minus sine squared u theta, sorry, not u, times sine squared theta plus cosine squared theta. This right here I notice is a difference of squares, which is, actually, I think I'm just going to leave it. Because what do we have from up above? Isn't that equal to my double angle, cosine of 2u? I guess I could factor it more, but that would probably leave me with more work. This is a Pythagorean identity of 1. So now we just get the cosine of 2 theta is equal to the cosine of 2 theta. Makes it a lot easier, huh? Than factoring that out and then going from there. All right. Example number 3 gets us into double angles geometrically speaking. So given a triangle at the right, find each of the following. So if I use the Pythagorean theorem, I get my hypotenuse to be the square root of 17. So now we got to find sine of 2 theta. So the sine of 2 theta is equivalent to 2 sine theta cosine theta. Well, the sine of theta is opposite over hypotenuse, so 1 over the square root of 17. Bring down that 2. My cosine of theta is opposite or adjacent, so 4 over the square root of 17. When I multiply all that across, we end up getting 8 over just 17, right? Cosine of 2 theta is equivalent to cosine squared theta minus sine squared theta. So my cosine is 4 over the square root of 17, and then I'm going to square that, minus my sine, which is 1 over the square root of 17, and then I'll square that. So squaring those gets you, what, 16/17 minus 1/17, so 15/17 will be your final answer there. Your tangent of 2 theta, so tangent, our double angle says it's 2 times the tangent of theta all over 1 minus tangent squared theta. Okay, so 2 tangent, so the tangent is opposite over adjacent, so 1/4 all over 1 minus 1/4 squared. So that gets me 1/2 divided by 1/4 squared is 1/16. 1 minus 1/16 would be 5/16. So then, or not 5, 15/16. Multiplied by the reciprocal. 16 over 15 would get you 8/15. There you have your final answer. Not too shabby. Okay, so now let's use some of our half angle identities. So given that u divided by 2 is equal to 165, find the following. Well, let's just keep this in mind. If u divided by 2 is equal to 165, then u itself should be equal to 330 degrees, right? Because I can double both sides. So using our half angle identity, remember our half angle of sine flipping over the front is 1 minus cosine u all over 2. And so we have our u being 330 degrees all over 2. So now if I use my unit circle to figure out where I am at 330 and what my x coordinate would be, it's at root 3 over 2 all over 2. Okay, so my numerator, that would really be 2 over 2. So I get 2 square roots of 3, 2 minus the square root of 3 all over 2, being divided by 2, really is 2 minus the square root of 3 all over 4, but then that whole thing's being square rooted. So if I square root the numerator, I get the square root of 2 minus the square root of 3 all over the square root of the denominator, which is 2. So we get that as our final answer. For part B, our cosine half identity, and again, I don't have these memorized, so that's why I'm flipping back over, is equivalent to the square root plus or minus the square root of 1 plus cosine u all over 2. Okay, so now what we're going to do is, okay, so if u is at 330, what are we going to be doing here? I want the, okay, so let's just work this. So 1 plus the cosine of 330 all over 2. And if I think about my cosine half angle, 165 would put me in quadrant 2, all students. So my cosine is going to end up being negative, so I want to put a negative in front of this. Okay, so here we go. We got square root of 1 plus the cosine of 330 is the square root of 3 over 2 all over 2. So that becomes the square root of negative square root of 2 plus root 3 all over 4, which would be the negative square root of 2 plus root 3 all over 2. That 2 not being underneath the square root sign. Okay. If we do our tangent of our half angle of 2, out of all the variations, we probably want to use the one that has, well, they both have cosines and sines in them. I think what I'm going to do is use the second option of 1 minus, is it cosine on top? Yeah, cosine u all over sine u. So then I get 1 minus the cosine of 330 all over the sine of 330. So I get 1 minus root 3 over 2 all over the sine of 330 would be negative 1/2. So then I get 2 minus root 3 all over 2 being divided by negative 1/2. So my 2's would cancel out, and then you'd be left with 2 minus root 3 over negative 1. So we get negative 2 plus root 3. I ran out of space there. Oh, it doesn't even like my fingers anymore. So negative 2 plus the square root of 3 is what that says down there for your final answer. Okay, so we got our half angle identities. Now our power reducings. So we're going to rewrite the cosine to the 4th power of theta in terms of trig functions with no power greater than 1. Okay, so what they're showing us here is that a power of a power. So cosine squared theta squared is the same as cosine to the 4th. So we know that if I use my power, where are they? My power reducing formulas, cosine squared itself is 1 plus cosine 2 theta all over 2 squared. Right? Is everybody okay with that? Now keep in mind, that's the same as just multiplying it out twice, right? Isn't it the same as just doing 1 plus cosine 2 theta all over 2 times 1 plus cosine 2 theta all over 2, right? It's just being able to write it twice. So if I multiply those two together, I'm going to get a 4 in my denominator, and then when I multiply my numerators, I'm going to be doing 1 plus cosine 2 theta squared. Okay, so I'm going to factor out that 1/4, so I don't have just one big fraction. And then I'm going to multiply, FOIL this out. So squaring the 1 would get me 1. My middle term would be 2 cosine 2 theta, right? I got 2 thetas in there, yes. 2 theta plus cosine squared 2 theta. Okay, is everybody good there? So I just FOILed out the numerator. Right here, cosine squared 2 theta. Well, if I think about 2 theta and cosine squared, and using my double angle theorem, is that what I want to be doing here? Yeah, because cosine squared is 1 plus cosine 2 theta, right? So this is the same as 1 plus cosine, using my power reducing formula, cosine 2 theta, but I already have a 2 theta there, so I'm going to double what's already there, which makes it 4 theta all over 2. Okay, everybody see that? All right, so now my next move is going to be down here. So now I have my 1/4. To get rid, so I'm going to keep this, we'll do this. So 1 plus 2 cosine 2 theta plus factoring out that 2 would make it a 1/2 times 1 plus cosine 4 theta would be my next move. Now I'm going to take out a 1/2 from everything. So I'm going to factor out that 1/2. I'm going to have to move up here. I'm running out of space. All right, so I'm going to get rid of all those fractions. So if I take out a 1/2, that's going to make the 1/4 and the 1/2 multiply to be a 1/8, right? If I take out a 1/2, then this means it's going to have to be a 2 to go back, plus, whoop, plus 4 cosine 2 theta plus 1 plus cosine 4 theta. Is everybody okay with what I just did there? So if I went and double everything, right? Would that be what I just did there? 1/8 to double, 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 doubling. I don't think if I doubled it, I would get 1/8, would I? Wouldn't I get 1/2? Yeah, I think I did that wrong. Right, to get rid of my fractions, double this, double this, double this. So that would get me 2. Yeah, so this should be 1/2. So that gets you 1/2, right? Double, 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 doubling everything to get rid of my fractions. Okay, so now we're there. And then the last thing I'm going to do is just combine my like terms. So we get 1/2 times 2 plus 1, which is 3, plus 4 cosine 2 theta plus cosine 4 theta gets us our final answer right there. Okay. Whew. All right, example number 6. So solving out algebraically. So we're going to solve the cosine of 2x to equal 1/2. We need to solve for x, and we're told that x has to be between, it's just one rotation, so between 0 and 2 pi. So we know that cosine of x is equal to 1/2 at pi over 3 and 5/3 pi. Okay. So now we're going to go for our cosine of 2x. Well, so we know that 2x needs to end up equaling pi over 3, and 2x needs to equal 5/3 pi. Okay, and then we know that it's going to do a whole nother rotation. Okay, so it's going to double it out. So now we're going to be going another rotation. So from 0 to 4 pi. So adding another full rotation would get me to 7/3 pi. Adding a full rotation to 5/3 would get me 11/3 pi. And so when I solve all those out, I get x has to equals, dividing out your 2's, pi over 6. Dividing out your 2's, 5 pi over 6. Dividing out your 2, 7 pi over 6. Dividing out your 2 gets you 11 pi over 6. So those would be all your values of x. Okay, so what happened? So we figured out where our cosine of x would be at 1/2. And then since we're doubling it, we're going to double our rotation. So instead of just going from 0 to 2, we're going to go 0 to 4 pi. So I have to figure out what all those coterminal angles would be in those rotations. For example 7, we have sine of 2x is equal to 0. So the sine of 2x is equal to 0. Since we're doubling it, we're going to be looking between 2 rotations now. So we know that we have to have, so sine of 2x is equal to 0. So 2x is going to be equal to 0. Where else are we at? 0. So sine is 0 at 0. It's 0 at pi. So 2x needs to equal pi. It would then be 0 again at 2 pi. And then it would be 0 again over at 3 pi. So when I solve all of those for x, we get 0, pi over 2, pi, and 3/2 pi. Would be all your values of x. All right, example 8, solve, find the general solution. So we have the cosine of 2x plus cosine of x is equal to 0. All right, so let's go ahead and turn these into things. So cosine of 2x, looking at my double angle cosine, so I've got multiple options. I think I'm going to go with, which one do I want to go with? 2 cosine squared x minus 1. So 2 cosine squared x minus 1. The reason why I'm going with that one is because I already have a cosine x in my equation. So then maybe I can try to factor this out. So if I rewrite that as 2 cosine squared x plus cosine x minus 1 is equal to 0. Try to factor that. Well, that factors to 2 cosine x. So if you just want to do like a u substitution, if we let u equal cosine x, that would be 2u squared plus u minus 1. So then you should be able to see that that's going to be 2u minus 1, u plus 1 when you factor it. So 2 cosine x minus 1 cosine x plus 1 is equal to 0. Using your zero product property, 2 cosine x minus 1 has to equal 0. So that gets us cosine x has to equal 1/2. When does cosine x equal 1/2? Well, at pi over 3 and 5 pi over 3. And then over here, cosine x needs to equal to -1. When does that happen? Well, it happens at pi. So in general, our general form, I guess I shouldn't say form. In our general circumstance, x is going to equal to pi over 3 plus each full rotation, right, where n is an element of the integers. And x is going to be equal to 5 pi over 3 plus every rotation, 2 pi n. And x is going to be equal to pi plus every rotation. Okay, so you just can keep adding it all the way through. So what are we doing? So we're adding multiples of a third each time, ultimately, right? So a third, so we're doing multiples of a pi over 3, so x is equal to, let's just leave it like that. I'm just going to leave it there. Okay, so there would be our general forms. These would be our exact answers within a specific domain, right? All right, I think that concludes our notes. All right, bye guys.